We saw chiral carbon using structural formulae, and we also saw how in displayed formulae you could identify chiral carbons. I told you benzene has no chiral center or a chiral carbon. Yes. Now let's see how we will identify chiral carbon in ringed structures. And then we will go over the homework questions, all right? So let's see. Now, if you have ringed structures, how will we identify chiral centers or chiral carbons in that? I told you benzene ring has no chiral carbons. So let's see if you have something like this. So for example, I give you a ring structure, a cyclohexane, right? And then this has a CH3 sticking out. There's a Cl here. There's an OH over here. Yes, let's suppose we have this. Now, if you have to find out, this right here is a CH3. Yes, I'm not writing the CH3 because you know one stick in a skeletal formula represents a CH3. Yes, so I'm just, okay, for your clarity, I'm just writing it down so that you can identify it. Now let's see, we got to identify the chiral carbons. So for that, we have to look at each carbon, all right? First, you look at this carbon. Can this be chiral? No, why? Because it has 3 hydrogens and it needs to have 4 different groups. So if it has 3 hydrogens, you just ignore it. Then you come to this carbon. Can this be chiral? Let's see, we'll see. Then we have this carbon. Can this be chiral? No. Why? Because this carbon is already making 1,2 bonds. So the third and fourth will be a hydrogen. So this has 2 hydrogens. Can this be chiral? No. We still have to check this one, all right? But we know that this one is not chiral. Yeah. We'll check this one later. We'll check these later. Let's check this. Can this be chiral? No. 1,2 bond, third and fourth will be a hydrogen. Can't be chiral because you need 4 different groups. This has 1,2 bond, third and fourth will be hydrogen. Can this be chiral? No. So we are left with only 3 carbons, which is this, this, and this. We need to identify whether these are chiral or not, right? So let's see. How will we identify whether these are chiral or not? Let's go by 1 carbon at a time. Let's look at this. Now this has 1 bond, 2 bond, 3 bond. Fourth will be a hydrogen. Now you know one is a hydrogen, one is a CH3. Are they both different? Yes. Now you got to identify the third and the fourth. What is the third and the fourth? We don't know what is this and this. We don't know that, right? So what will we do? We will make a line of symmetry. What will we do? Make a line of symmetry. You got to compare between this carbon and this carbon. On this carbon, you will draw a line of symmetry between these. Yes. And do you see? One was a CH3, one was a H. Then one is all of this. Do you see this is different from the CH3 and the H? And it's very evidently different because there's an OH sticking out there. And the fourth group is all of this. Do you see this is also different because it has a Cl sticking out? Yeah. Now, what you guys usually think is, you think, oh, one is a CH3, one is a H, one is a C, one is a C. Oh, same. No, it's not just this C, it's this whole thing up till here, which is the third bond. And this whole thing from here to here, which is the fourth bond. Yeah. So you have this. So what will you do? How will you identify it? By drawing a line of symmetry between them. One is a CH3, one is a H, one is all of this, and the fourth is all of this. Do you see all 4 are different? Yes. Is this clear? So this will be chiral. Yeah. All right. So this is chiral. So I'm making an asterisk here. This is chiral. Got to check this one. Let's see this one. So you have 1 bond, 2 bond, 3 bond. Fourth will be a hydrogen. Now, one is a H, one is a Cl. We can clearly see they are different. Between this and this, let's see which one. Are they different or the same? So you make a line of symmetry. Do you see this side is different from this side? Why? Because there's a CH3 sticking out here. There's no CH3 sticking out here. Yes. And you know that all 4 bonds are different. So this will also be chiral. Then we have one last carbon, which is this one. Let's check this. Is this chiral or not? So you have 1 bond, 2 bond, 3 bond. Fourth will be a hydrogen. So what will we do? To check the third and fourth, we will draw a line of symmetry. Do you see this side is different from this side? Yeah, there's a CH3 there. There's a Cl on the other one. Yeah? This is different. So this will also be what? Chiral? Yeah? Is this clear? Do you understand this? So this one has how many chiral centers? 3 chiral centers. If it has 3 chiral centers, how many total optical isomers will it have? Total optical isomers would be 2 to the power n, where n will be the number of chiral centers. So this will be 8. Is this clear? Do you understand this? All clear. Now let's see the homework that I gave you. Which compound is both chiral and acidic? For acidic, which group do we need? CO2H. So it needs to be a chiral center. Now for a chiral center, you must have carbon with 4 single bonds. Now you look at each carbon. What is a CO2H? A CO2H is like this. Yes, this is CO2H. Can this carbon be chiral? No. Why? Because it has a double bond. You need 4 single bonds. So every time you see a CO2H, you ignore it. It can't be chiral. Can this be chiral? No. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Double bond. Are there any chiral centers? No. Clear? Now, even if this has chiral centers, is this acidic? No, because this has no acid group. It has no CO2H. Don't bother. All right. Needs to be chiral and acidic. So must have CO2H. Let's check C. Now, let's see this. Now, most of you would think, oh, right here we have an acid. This is not acid. Which group is this? Ester. In acid, the H must be with the oxygen. If you have HCO2, that means it is this. And this is not acid. This is ester linkage. Do you understand this? Again, does this have any acid group? No. So we don't look for a chiral center. Let's check D. We've already eliminated A. So you see from the 4 options, you eliminate B and C instantly. Why? Because this has no acidic group, B, and C also has an ester linkage, no acid. Yeah, you can eliminate it. You are left with A and D. You check for chiral centers in A, there are no chiral centers, your answer will most probably be D. Let's check. Can this carbon be chiral? No. Why? Because it's a CO2H, it has a double bond. But it has an acid group at least. Can this carbon be chiral? Yes, because it has a H, an OH, a CO2H, and all of this. Are they 4 different groups? Yes. So can I say this is chiral? Yes. So this is chiral and acidic. Can this be chiral? No. Why? Because it has 2 H's. Can't be chiral. CH2 can't be chiral. But we have at least 1 chiral center and this is acidic. So the answer is D. Clear? Let's check the first one also. How many chiral carbons are present in the molecule of camphor? Can this be chiral? No. Why? CH3. Can this be chiral? No. 2 hydrogens. Can this be chiral? No. 2 hydrogens. Can this be chiral? No. 3 hydrogens. Can this be chiral? No. Why? 2 CH3s. Do you see that? Okay. Can this be chiral? No. Double bond. Can this be chiral? No. 2 hydrogens. You are only left to check this one and this one. Yeah. Let's check it now. 1 bond, 2 bond, 3 bond, 4 bond. One is a CH3. One is all of this. All of this. One is all of this. And one is all of this. Are they all different? Yes. And they're very evidently different. Do you see this one? I'm going to highlight it in different colors. The second bond, the third bond, and the fourth bond. Do you see? And this is the first one. Do you see they're all different? Yes. So can I say this carbon will be what? Chiral? So this is chiral. We had to check this also. Same thing. One is a H. This is the second. Let me highlight it. This is the second. Yes. This is the third. And this is the fourth. Are they all different? And this is the first. Are they all different? Yes. So can this be chiral? How many chiral centers? Clear? 3. How many structural cis and trans isomers are there for dichloropropene? C3H4Cl2. So you have C3H4Cl2. You need to draw structural and cis trans, right? So they are saying for dichloropropene, that means do you need alkane, cycloalkane? No. So first one, let's draw this where both the Cl's are on the first one. This is called what? 1,1-dichloropropene. Then you can have 1,2-dichloropropene. Then you can have 1,3-dichloropropene. Then you can have, what is this? 2,3-dichloropropene. Then you can have what? 3,3-dichloropropene. Is this clear? Yeah. Now we've made all the structural isomers. Now let's look for geometric. Can this show cis trans? No, you have a carbon-carbon double bond. This carbon has 2 Cl's. Can this show cis trans? No. This one, can this show cis trans? Yes, it has a Cl and a H, a Cl and a CH3. So this will exist as a cis and a trans. This one, can this show cis trans? HCl, H, all of this. Yes. So this also has a cis and a trans. Do you all understand how? Yeah. Can this show cis trans? No, because this has 2 H's. Can this show cis trans? No, 2 H's. How many total isomers? I think we've done this in class. 1, 2, 3, 4, 5, 6, 7. How many isomers? 7. Clear? Question number 4. Warfarin is used as rat poison. How many chiral centers are present in warfarin? Let's see. Now you know none of these would be chiral. Yeah, because in benzene ring, none of them are chiral. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Double bond. Can this be chiral? We'll check. Can this be chiral? No, it's 2 H's. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? 3 hydrogens. So you just have this to check. Let's see. Is this chiral? This has 1 bond, 2 bond, 3, and 4th. Yeah. So one is a H. Let me highlight them in different colors. One is a H. One is a CH2COCH3, the second bond. The third is this. And the fourth is all of this. Are they 4 different? Can this be chiral? Therefore, the answer is B. Clear? Do you understand this? How many alcohols, including structural and stereo, have the molecular formula C4H10O? So you need to make alcohols with the formula C4H10O. Let's make the first one. What is this? Butanol. Then let's make butan 2-ol. So this is butanol, butan 2-ol. Can you have a butan 3-ol? No. What will we do? Shorten the chain. The 4th carbon will go on the middle one, and this will become 2-methyl propan 1-ol. Then what can we have? A 2-methyl propan 2-ol. Can we have anything else? Any other possible structural isomers? Okay, now check for stereo. They can't have geometric because there's no carbon-carbon double bond. Check for chiral carbon. Can this be chiral? No. 2 H's, 2 H's, 2 H's, 3 H's. Can't be chiral. 3 H's. What about this? Can this be chiral? Sorry, what? Can this be chiral? OH, H, C2H5, CH3. Are they 4 different groups? Yes. Can this be chiral? Yes. So this will exist as how many isomers? 2. A D and a L. I'm just calling it DL. Whichever is D, we don't, care. Can this be chiral? No. Why? 2 H's. Can this be chiral? No, because it has a CH3 and another CH3. Not chiral. And can this be chiral? No. Can this be chiral? No. No chiral center. Then let's see. The last one, the 4th one. Can this be chiral? No. Why? 3 hydrogens. Can this be chiral? No. Why? CH3, CH3, CH3. Can this be chiral? No. So only one has a chiral center. So 1 isomer, 2 isomer, 3 isomer, 4 isomer, 5 isomer. Clear? Which molecule does not have a chiral center? Okay, let's check. Can this be chiral? No. Why? Double bond. CO2H has a double bond. Can this be chiral? Yes, a CO2H, a H, a OH, and all of this. Yeah? Can A be your answer? No, because they're saying which does not have a chiral center. This does. Also, if you check, this is also chiral. Do you see? H, OH, CO2H, all of this. So this is also chiral. Let's check B. Can this be chiral? No. Can this be chiral? Yes. It has a CO2H, H, OH, all of this. So this is chiral. Can this be chiral? Yes. H, OH, CH3, all of this. Yeah. So you have how many chiral centers here? 2. Let's check this. This one. Carbon has a OH, a CH3, all of this, and this. Is this chiral? Why? Benzene is on OH, but do you see the position of the benzene on the OH? Can you see the position of the OH on the benzene? Do you see this is on this carbon? Let's call this carbon 1, 2, 3. This, let's call this carbon 1, 2, 3, 4. Do you see they are different groups? Because the position of the OH is different. So this is chiral, yes. On the other hand, you see the position of this OH and this OH is exactly the same. So is this chiral? No, because this and this are the same. The highlighted pink ones are the same groups. So this does not have a chiral center. Clear? This is chiral. Understood? What is the number of isomers of C2H2Cl2 including cis trans? Why C is chiral? Because if you see here the OH, if let's call this carbon number 1, this one, carbon 1, carbon 2, carbon 3, carbon 4. The OH is attached on carbon number 4. And over here, this is carbon 1, carbon 2, carbon 3. The OH is attached on carbon number 3. So the position of the OHs are different. So they are different things. Just like butane 1-ol and butane 2-ol are two different compounds. Just like that, this and this are two different. All right. Now, what is the number of isomers of C2H2Cl2 including cis trans? Yeah. So let's see. C2H2Cl2. So C2H2Cl2. So you have one possibility where both the Cl's are on the. So this is 1,1 dichloroethene. What else can we have? 1,2 dichloroethene, and you can see 1,2 will show what? Cis trans. So this will be cis and trans. Why? Because we have a carbon-carbon double bond, two different atoms on each carbon. So how many total isomers? 1, 2, 3. Any other possibility? Yeah. Which molecule? Each with a linear carbon chain. Linear carbon means no branch, straight chain. Can have optically active isomers. So C3H6BRI. Now you have one BR, one I. They have told you it's a linear chain. You will try to position BR and I in such a way that you may get an optical isomer. Let me put the BR over here and let me put the I over here. Do you see this carbon becomes chiral? Why? Because it has a H, an I, a BR and a C2H5. So can you make this optically active? Yes. So one is possible. Then you have C3H4BRI. So there has to be a double bond somewhere because you have 6 atoms attached to 3 carbons. So there has to be a double bond. Now, if you have this double bond, let me attach the BR here, the I here. This is the H. Can this be chiral? Yes. Why? Because it has a BR, a I, an H, and it has C2H3. Is this chiral? Yes. Can you make this optically active? Yes. Then you have C3H6I2. Now 2 I's. Let's position them in such a way that you may get a chiral carbon. Do you see this carbon right here? Can I call this chiral? Because it has a H, an I, it has a CH3, and it has a CH2I. Do you see this is also chiral? Yeah. Then you have C3H4Br2. So you again have a double bond somewhere. Now putting it on these carbons is pointless because they can't be chiral anyway. Now you have 2 BRs. So if I put one BR here, it will do me no good because this can't be chiral, it will have 2 hydrogens. If I put both the BRs here, it will again do you no good because you will have 2 BRs. So can this show chiral carbon? No. So answer is 1, 2, and 3 only. Is this clear? Understood? How many chiral centers do you have in one molecule? Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Double bond. Can this be chiral? No. Why? 2 H's. Now we are left with only this and this. So let's check for this and this. Let's see. This has 1 H. It has 1 all of this thing. It has, now you have to check between this bond and this bond. So what will we do? We will draw a line of symmetry. Do you see this side is different from this side? Do you see it's very evidently different? The pink one has OHs, the blue one has ester. Yeah? One is a H and one is all of this. Are they 4 different groups? Yes. So can this be chiral? Yes. So this will be chiral. Let's check this. This has a H, it has a CH2OH, it has an OH, and it has all of this. Are they all different? Yes. So will this be chiral? How many chiral centers? 2. Understood. Yeah. Which alkene could exist in cis-trans form? So we need to look for what? Geometric isomerism. Can this be cis-trans? Can A be cis-trans? No, because this carbon has 2 hydrogens. It needs to have 2 different atoms or groups. So this can't be cis-trans. Let's see B. So B is C double bond C. B is C double bond C. Is this clear? So B will be the answer, not C because C has 2 H's here, not D because you have 2 CH3s here. It will be B, where you have a carbon-carbon double bond, which with a H here, CH3 here, yes, and the other one has a H and a C2H5. So this will show cis-trans. Is this clear? Is this understood? Kids online? Kids online, is this clear? How many chiral centers does each possess? So you have citric acid. Can this be chiral? No. Why? 2 hydrogens. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? Because it has a CH2CO2H here and a CH2CO2H here. It has a OH, it has this, and the 2 pink ones are the same. Not chiral. Can this be chiral? No. Why? Double bond. Can this be chiral? No. Why? 2 H's. Can this be chiral? No. Why? Double bond. Does this have a chiral center? No. So citric acid has 0 chiral centers. Let's check for this. Can this be chiral? No. Why? 2 H's. This, double bond. This, yes. This can be chiral. It has a H, a CO2H, a this, and a this. Are they all different? This is chiral. Can this be chiral? No. Double bond. Can this be chiral? Yes. It has a H, an OH, a CO2H, and all of this. Are they all different? Yes. Can this be chiral? No. Double bond. So how many chiral centers in this? 2. The answer is B. Clear? Which pair have identical boiling points? So you know that geometric isomers have different boiling points. Cis has more, trans has less. And if the number of carbon atoms are different, carbon, hydrogen, if that's different, then also they will have different boiling points. Yes, because the number of electrons will change and the strength of the van der Waals forces will change. So let's see. You have A and you have B. Let's see A. So A is a 4-carbon alcohol. What alcohol is this? Butanol. Yeah. What is B? I mean, this. So that is a C with a H with two CH3s and CH2OH. That's what this is? Yeah? C with a H and two CH3s. So C with a H, two CH3s, then a CH2OH, a CH2OH. Yes? Which alcohol is this? 2-methyl, 2-methyl, propan, 1-ol. Yes, the main chain is of 3 carbons. Will they have different boiling points? Yes, even though their molecular formula is the same, but they will have different boiling points because the strength of intermolecular forces will be different. I told you it depends on the number of electrons and surface area. This has greater surface area. This has less surface area. Yeah. So will they have different boiling points? Yes. So for these, it would be different. Then you have CH3, CH2, 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 and a CH3. This is what? Hexane. Yeah. And then you have a CH with 2 CH3s. This is probably a branch, yes? A CH with a CH, CH with 2 CH3s. So with 2 CH3s like this. The first one was 6 carbon straight chain. This right here is 1, 2, 3, 4. This is what 2,3-dimethyl butane. Will the boiling points be different? Yes, because this is greater surface area, less surface area. So this is different. So this is also different. Then optical isomers, you know their boiling point is same. What is different? Arrangement is different, and what is different? Their effect on polarized light. So they will have identical boiling points, and you also need to see, are they optical isomers of each other? CH3, CH3. H to the left, H to the right. Cl here, Cl here. This is to the right, this is to the left. Yes, they are optical isomers and they will have identical boiling points. In cis trans, if you see D is which isomer? This one is trans. Similar atoms on opposite sides. Similar atoms on same side. This is cis. Cis trans have different boiling point. The answer therefore is C. Identical boiling points is C. Question number 14, number of chiral centers. Can this be chiral? No, why? 2 H's. Can this be chiral? Yes, why? H, OH, and this. Yeah, and all of this. Are they different? Yes. Can this be chiral? Why? H, OH, this, and this. Yeah. On the top, you have 2 carbons. At the bottom here, you have 3. So this is also chiral. Can this be chiral? Yes. H, OH, 3 carbons here, 2 carbons here. This is also chiral. Can this be chiral? Yes. H, OH, 4 carbons at the top, 1 at the bottom here. Yes, it is chiral. Can this be chiral? No. Why? 2 H's. How many total chiral centers? Is this understood? Do you guys get this?